All right. Well, thank you, everybody. Welcome to today's webinar on designing a timber beam using AS1720.1. We're going to talk about the complete design process for designing a timber beam, as well as some of the differences to AS1720.3 and 1684. So as an outline of our presentation today, first I'll give you a bit of an introduction, then talk about the differences between AS1720.1 and 1720.3 or 1684. I'll then go into the meat of this presentation, which will be about designing a timber beam, talking about the characteristic properties, modification factors, bending capacity, shear capacity, bearing capacity, and deflections. I'll also give you a couple of example calculations before concluding and taking questions. So first, a bit about me. My name is Brooks Smith. I'm a chartered professional engineer. I have a master's in structural engineering. I'm a member of Engineers Australia. I'm also licensed in the United States as a professional engineer. I'm currently the engineering development lead for ClearCalcs, and I've held that position for about 1.5 years now. Timber Beam is our longest standing calculator in the system, and we figured it was about time that we actually ran a webinar on it. I also have 8 years of previous experience before ClearCalcs, working in research and development consulting, where I specialized in cold form steel, and a research fellowship in the system behavior of thin-walled steel, and I worked as a forensic structural engineer on commercial and residential structures, where I specialized in reinforced and post-tension concrete. So first, this is the only slide I'm going to show you that's explicitly talking about ClearCalcs, but we are providing you this webinar for free. So we think we have a great product with ClearCalcs because we have very easy to use design calculators for concrete, steel, cold form steel, and timber, all fully backed by finite element analysis, giving you the most accurate possible results for all of your designs and analyses. We help eliminate wasted time by allowing you to automatically size your members, link loads between your members, and for our top tier customers, import your CAD drawings directly into our platform. We're also available everywhere because we're cloud-based, so you can work effectively and just as well from the office, home, or site. So if you're quarantined with coronavirus, you can use us from home just as easily. Fortunately, that won't give you an excuse to not work. So today's goals, I want you to leave this webinar being able to design a timber beam according to AS1720.1 with the latest amendment up to Amendment 3. In order to fit this webinar within roughly an hour time frame, we're going to make a couple of simplifying assumptions. First, we're going to assume a rectangular cross section. I'll point out a couple of places where you need to make modifications for round timber, but I'm not going to be focusing on that. I'm going to basically ignore plywood entirely. Plywood is serve its own beast within the standard, so take a look at that section yourself if you are interested in plywood designs. I'm going to assume that the beam is neither notched nor tapered. Generally, for a notched or tapered design, you're going to go through this full process I'm going to talk about, but then just make a couple of modifications at the end. So most of this is still going to be relevant. You're just going to do a couple of extra steps with a notched or tapered beam. I'm also only briefly going to address detailing. Again, see the more construction-focused standards if you're interested in that. We will be distributing this slide deck and the video of the webinar afterwards. Expect that next week, though, as our video editor on staff is on holiday right now, so that will come next week. But we will be distributing that, so you can expect that in your email. I prefer to ask questions as I go along. I prefer to answer while I'm on topic, so do feel free to ask questions at any time. I do ask that you please use the Q&A feature of Zoom and not the chat or messaging feature. It's just easier for me to keep track of what I have and haven't answered if you use the Q&A feature. If you do have particularly involved questions, again, feel free to ask those at any time, but I may save those until the end of the webinar, just to try and keep within the time frame of this webinar. And a quick note, everything today is based on the standards. While I am involved with Standards Australia, none of us in ClearCalcs are on the committee for AS1720. We're not speaking for them, nor communicating any special knowledge. So if something I say does contradict with what's in the standard is what governs. So moving on to differences to AS1720.3 or 1684. So first off, AS1684.1 is a defunct standard now. If you have a copy of it still, you should toss it in the bin right now. It was replaced in 2016 by AS1720.3. AS1684.2, .3, and .4, parts 2, 3, and 4 do still exist, but those are the construction standards. They are not the structural design standards. So 2, 3, and 4 are specifying things like door size, rise over run of steps, how many smoke detectors you need to have, things like that. They're not structural design. AS1720 series is all the structural design. So as to the difference, the key quote is at the beginning of AS1720.3 here. And it says that 1720.3 is an interpretation of the AS1170 series, AS4055, and AS1720.1. So it's an interpretation of the load standard, the residential wind standard, and the main timber standard. That's only applicable when using the conventional timber framing system described in AS1684.2, 3, and 4. So there's no new information provided in AS1720.3. It's merely conglomerating about 7 other standards into one document. And in order to do so, it's being more restrictive, and I'll talk about that now. So the ways 1720.3 fits all of that information into one document is it's much more restrictive. You can only design a class 1 or 10 building, refer to the NCC for the exact definitions, but that basically means houses or farm structures that are constructed according to AS1684.2, 3, or 4. So that are using just a conventional repetitive timber framing system. 1720.1, no restriction. Any structure made of timber you can design. In point 3, you only have standard grades supported. So your F grades, MGP, A17s, only those are supported in 1720.3. There are specific LVLs that are supported in 1720.3, but you have to see the manufacturer. The manufacturer has to formally say that 1720.3 is supported for their LVLs. In point 1, any timber product. Well, almost any timber product. CLTs aren't supported yet in any Australian standard. And the load calculations, all of your load cases, all of your load definitions are self-contained within 1720.3. If you're designing with point 1, you have to go instead use the separate standards. You have to use the 1170 series or AS4055 for residential wind loads for all of your load and load cases. The biggest restriction, though, with 1720.3 is in the size and features of the building. So only specific roof types are allowed with 1720.3. So if your roof is too steep, you can't use 0.3. If you have more than 2 stories, you can't use 0.3. If you have any wall height that's greater than 3 meters, or if any dimension of your building is greater than 16 meters, you cannot use 0.3. You have to use AS1720.1 if your building you're designing does not fall within these restrictions. So why would you use AS1720.3 if it's so much more restrictive? Well, it is easier to use. If you're doing hand calculations, if you're writing your own Excel spreadsheets, it is simpler. It's also completely self-contained. You don't need to buy any other standards. So if you're just starting your own practice and don't have a lot of money to spend $5,000 for your standards, you can just buy this one and you'll be able to handle many residential houses. 1720.3 also has value in just being a reference. It's a good reference to look at for information on just what the typical loads and restraint configurations are like for different types of timber beams. So even if you aren't actually designing according to 1720.3, builders around Australia are often used to constructing houses that are designed to it. So to avoid mistakes in construction, it can sometimes be best to just use the same restraint configuration and such that 1720.3 calls for. Even if you're not actually designing with it. So it's a good reference to have. It does have its place, but we're not going to be talking about anything more with how to use it here. It is a fairly self-explanatory standard. We're going to dive into 1720.1. So first, for designing to the main timber standard, 1720.1, you have to find your characteristic properties of your timber member. You have to calculate, let's start from the beginning. To design a timber beam, you have to calculate your demands first, according to AS1170 series. Then you have to find your characteristic properties, then calculate your modification factors. I suggest calculating all of your modification factors first before bothering to do any of the capacity checks. Once you have those modification factors, then you calculate your flexure, shear, bearing, and deflection, and make sure that everything is within limits for the beam that you're designing. So what are characteristic properties? Every grade and species of timber has its own characteristic properties. These are the things that don't change based upon the design conditions. They are constants. Some of those are defined by various parts of the standard by 1720.1. Some are defined by manufacturers. They include characteristic strength values, the 8 values shown here on the left for bending, shear, bearing, compression, tension capacities. It may become 11 characteristic strengths for some laminated members or oriented members. You may have different bending, shear, and bearing strengths for major and minor axis bending, but usually you're just going to have 8 characteristic strengths. You also have characteristic average values for the modulus of elasticity, the modulus of rigidity, and the density of your timber member. But how do we get those values then? The simplest are MGP and A17 grades of timber. If you have one of those, then you simply look up the characteristic properties in a single table, table H3.1 and appendix H of the timber standard. So this is just going to show you your different stress grades and various section sizes. If you have a size that's in between what it lists here, then you can interpolate between those. But simply look in this table, that's all of your characteristic properties, done. For F grades, most of your characteristic properties are dependent upon the grade only. So in table H2.1, you can look up the characteristic properties based upon whether you have an F4, F34, F17, and whether you have a hardwood or a softwood. This table will tell you most of those. If you have a particularly large member, if your depth is greater than 300 millimeters, then you multiply the F prime B, the characteristic strength and bending, times 300 divided by D to the power of 0.167 here, as shown in the lower right. Similarly, if you have a beam in which any dimension is greater than 150 millimeters, then you multiply that characteristic tension capacity, characteristic tension strength by the formula shown here. For round timbers, you have some additional modifications you have to make, and refer to clause 6 for those. But these aren't all of the characteristic properties. You still need to look up your bearing, density, shear at joint details, and tension perpendicular to grain. And those come from a different set of tables that are dependent upon the species of timber. So in order to find this, there's a long table in Appendix H, table H2.3. I've only shown a small segment of it here on the left side that will tell you all of the different species available and the strength group that each is associated with. So what you're interested in is this strength group. So say I have a seasoned mountain ash that I want to design. That tells me that it's strength group SD3. I then go to table H2.2 and look up SD3 and look at the row here for finding my bearing, shear joint details, and tension perpendicular to grain values. So a two-step process to find the rest of your characteristic properties for an F grade. Then for glue lambs, you have a similar process as for F grades. Most of the characteristic properties are dependent upon the grade, and you just look up in table 7.1 what those characteristic properties are. You have a similar modification you need to make for that characteristic tension strength, though you don't have a similar thing for bending. It's only for tension here for glue lambs. You'll notice that bearing, density, shear joint details, and tension perpendicular grain still aren't listed here. Those, again, are dependent upon the species. So for glue lambs, just as for F grades, you need to refer to tables H2.3 and H2.2, same as we did for F grades, to find the remainder of your characteristic properties. Finally, if you're designing an LVL member, the standard tells you that the characteristic values for LVLs shall be obtained from the manufacturer. So there's no guidance in the standard for this. You have to go to the manufacturer. A couple of examples are shown here. You need to find which publication they've actually listed these things in. Sometimes that is a bit hard to find, unfortunately, but they all publish it somewhere. So a couple of examples here for Carter Holt Harvey high spans and LP Building Products Solid Start. There's some other manufacturers out there as well. For plywood, see clause 5. That just defines everything in that clause. There are some engineered timbers, such as CLTs, which are not defined in any Australian standard, unfortunately. If you're trying to design with a CLT, you have to do performance-based design right now. Unfortunately, there is no Australian standard supporting it yet. The committee is in the process of working on adding those, but it's going to be a bit of time until we have a standard that defines CLTs. You do have some modifications you need to make to LVLs. The standard tells you that unless the manufacturer says otherwise, you have to do the same bending and tension multiplications that you did for F grades for LVLs. Although I've never actually seen a manufacturer that fails to tell you this. So you can just refer to the manufacturer. They're going to tell you the formulas that you need to use to modify your bending strength or your tension strength, given what they give you in the tables. So there's your characteristic properties. Next, we'll move on to modification factors, which will actually be the bulk of your calculations. So almost half of this presentation is going to be just talking about the various modification factors, which we'll dive into now. So first off, there are a lot of modification factors. What they are values that you multiply by the characteristic property and a geometric property in order to get the design capacity. So the standard doesn't give you a table like this, although the equivalent US standard does, and I find it helpful, so I figured I'd reproduce one for you here for Australia. So for Australia, these are all of your different limit states listed on the left, all of the relevant modification factors in the middle, characteristic property, and the geometric property that you have to multiply together. So for example, to get your bending capacity, multiply the capacity factor, your phi value that you're all used to, times K1, times K4, times K6, times K9, times K12, times characteristic strength and bending, times the section modulus. And that will be your bending capacity. The one thing I'll point out here, I put a little asterisk next to K12 because I think it would be clearer if they actually listed this as two different modification factors. The K12 value for bending and the K12 value for compression are essentially unrelated. They're two completely different numbers. Those are different numbers. Everything else, these will all be constants for every limit state. So the K6 value will be the same K6 value for each limit state here for bending, shear, bearing, etc. So what those modification factors are, we'll start with the phi factor, the capacity factor. In timber, you have a structural category that's defined in the timber standard. This is essentially the importance of the member you're designing and the importance of the structure you're designing in. Usually in houses, your bearers are going to be category 2 and everything else will be category 1. Category 1 is essentially a member that if it fails will only cause a small amount of damage. Category 2, if it fails, a significant portion of the structure may fail. And category 3 is one that probably few of you will ever touch. It's for if you have a primary member in a hospital or some other post-disaster structure. So generally, you're not going to touch category 3. Look up in this table what your phi factor is. You'll notice that for category 1, they're all 0.95 or 0.90, depending on the grade of timber that you're designing. One thing I'll point out here, though, for category 2, for your bearers, you have a phi factor of 0.85 if you have an MGP 15, F17, or higher grade. But if you have anything lower than that, your phi factor is 0.7. So essentially a standard is trying to really incentivize you to use a relatively high stress grade for your main members in your building. If you don't, this is giving you an almost 20% penalty right off the bat. So if you can, use a relatively high stress grade for your main members in your building. Next, the duration of load factor, the K1. This factor applies a penalty to longer term loads. Timber is able to withstand impacts or other shorter term loads much more easily than it can longer term loads, permanent loads that are on top of it. So for each load case, clause 241, the main clause talking about modification factors, gives you a long list of notes and tables based upon durations that you can go through to find out what the appropriate K1 factor is for each load case. But much easier is to just look at Appendix G of AS1720.1. In here, table G1 gives you just a nice table of all of the load cases defined in AS1170 and what the K1 factor is that you should use for each of those load cases. Now note that for your main gravity load case, 1.2G plus 1.5Q, there are 4 different possible K1 values depending upon whether it's a roof or floor you're designing and whether it has distributed or concentrated loads. So take a look at this. You do use the smallest value here. So if you have a floor with both distributed and concentrated loads, then you would use 0.8 for the entire load case. You would not use a bit of each. You'd use 0.8 for the whole thing. So you take the worst case, K1, for the entire load case. Now, for some reason, table G1 doesn't include the snow load cases. So I've just appended at the bottom of this slide here what that would look like for the snow load case. For that snow load case, the K1 value you use depends upon whether you're in an alpine area or a subalpine area. Basically with the idea that in an alpine area, you may have snow that's sitting on top of the building for a month at a time. So you'd use a lower K1 factor in alpine areas instead of subalpine. But yeah, basically refer to table G1 as well as my additions here for snow loads. Now there's a really critical note that's listed in small text in clause 241 that I want to highlight here. And that's saying that the critical load combination may not be the one with the highest demands in timber. This is really unique. This makes timber unique among materials. In steel, in concrete, in cold form steel, in aluminum, you calculate one capacity and then compare all of your demands from every load case to that one capacity. In timber, you have a different capacity for each and every load case. So you have to calculate several different capacities. And that means that the load case with the highest demands doesn't necessarily govern your design. If you have a member you're designing that has a particularly high dead load relative to its live load, then even if 1.2 G plus 1.5 Q gives you a higher demand, 1.35 G might govern here because that does have a much smaller K1 value. So this means that you do need to calculate your demands and capacities for every load case, not just the one with the highest demands. So moving on, moisture condition, that's your K4 factor. This applies a penalty to seasoned timber that's used in moist conditions, or it applies a benefit to small cross-section unseasoned timbers that are given the chance to dry. So first, for unseasoned timber, usually your K4 value is going to be 1.0. The exception is if you have a beam that won't be fully loaded until it has partially seasoned to below 25%, as the standard says, moisture content. If that's the case, you use table 2.5, and depending upon the dimensions of your member, you use a K4 value shown in the table there. So what actually does that mean though? That means that if you're using an unseasoned timber and it's going to be underneath a roof, it's going to dry a lot during construction, then you can probably take advantage of this. But different timbers dry at different rates, different species dry at different rates. So talk to your retailer or distributor and ask them how fast the particular member you're using might dry, and see if you can take advantage of this K4 factor boost here. This could give you up to a 15% boost in capacity if you're using an unseasoned timber. If you're using a seasoned timber, then again, usually your K4 value is going to be 1.0. That is, unless your beam's average moisture content for a 12-month period, known as the equilibrium moisture content, may exceed 15%. If that's the case, then you calculate your K4 value based upon the greater of the two equations shown on the upper right here. So again, what does that actually mean? If you have a seasoned timber that you are using in a situation that's not protected from rain, for example, on a patio, or if it's for a building right on the ocean and might get ocean spray, then you should probably make use of this clause. Probably your moisture content is going to increase. I'd also use this if you have, for example, an exposed timber in a bathroom, because the steam from regular showers will keep the moisture content in that room relatively high. But again, talk to your retailer or distributor as to how quickly the particular seasoned timber you're using may absorb moisture. Also, as a note with this, you can't count on cabothane or polyurethane or any other sealant here. You are supposed to assume that your users are not maintaining the timber. You're supposed to assume that the residents of your building are just going to leave it as is. So this should take into account the native properties of the timber, not any post-installation treatments. For an LVL, it's very similar as for a seasoned member. Again, K4 is usually 1.0 unless that equilibrium moisture content might exceed 15%. If that's the case, then you refer to table 8.1 here. Those of you who are particularly eagle-eyed can do math quickly in your head may notice that the bending and compression line here is mathematically equal to the conditions for seasoned timber here. So for bending and compression, we'll come up with exactly the same number. If you have tension or shear forces, you do have a different K4 that you make use of for LVLs only. Your K6 factor. In most cases, this is going to be the simplest modification factor of all of them. For most of Australia, your K6 is simply 1.0. The exceptions are for if you are in the far north or in coastal Queensland, in which your K6 is going to be 0.9. There are also some specific localities that may specify a different K6 value as well. Check your specific locality for this. But in general, cities such as Darwin, Cairns, Townsville, they'll all have a K6 of 0.9 that you should be using in timber design. Next, K7. This is your length and position of bearing. Effectively, this factor makes small interior bearing areas less disadvantageous. Note that I'm saying less disadvantageous here. It doesn't actually provide a benefit. You are always better off with a larger bearing area, but this just makes it hurt less if you have a small bearing area on the interior of a beam. So what it accounts for is load spreading within the beam. So if you have a small bearing area in the interior, load's going to spread out like a V a bit. So you're going to have a slightly higher bearing capacity than you would if you're just taking into account the gross area of your bearing. It's only relevant for interior bearing though. So for end bearing, which means according to the standard, if you are less than 75 millimeters away from the end of the timber, you just have K7 of 1.0. You can't take advantage of anything here. For interior bearing, so if you're more than 75 millimeters away from the end of the timber, then you look up in table 2.6 what your K7 would be for various bearing lengths. So this can give you up to a 75% boost in your bearing capacity. Length of bearing, as defined here, is measured parallel to the grain. Usually that just means along the length of the beam, but just make sure the direction of your grain here. It's equal to the diameter if you have a round bearing area. So just straight use the diameter and don't worry about grain direction if you have a round timber. Next, strength sharing factor. That's your K9 factor. If you are designing a glue lam, an LVL, or plywood, your K9 is just always 1.0. The standard assumes that those laminated members effectively have already taken a K9 into account because of their laminations. You can't take any further benefit from the K9 factor with glue lams or LVLs. This factor, however, does give benefit to F grades, MGP grades, or A17 grades, in which you have either a combined parallel system, as the standard calls it, basically meaning if you have multiple members fastened together, then you can take advantage. The standard does not actually say how many fasteners you need or any more specific clause for how well fastened that needs to be. The only guidance it gives is that it says that all of the elements have to be constrained to the same deformation under load. So if you only have one fastener in holding these laminates together, you probably can't take advantage of this. But use your engineering judgment or do some calculations to make sure that your deformation is going to be the same for all of your members in this laminate, and then you can take advantage of it. Also allows you to take a benefit if you have a discrete parallel system, so repetitive framing. For this, if you have multiple parallel members, at least 3 parallel members, then you can also take advantage. The one additional requirement is that you have to have an overlying set of members. So for example, small rafters or purlins on top of your members, or you have to have sheathing on top of there and it has to be fastened. But if those conditions are true, If you have sheathing or overlying members and at least 3 parallel members, then you can take advantage of this as well. So question about calculating the laminating of 2 LVL beams. Again, for LVLs, K9 is just always going to be equal to 1.0. You're not allowed to take advantage of this modification factor if you have an LVL. For 2 timber beams of other grades, of an F, MGP, or A grade laminated together, then you can take advantage of this. Your NCOM value, N sub COM value, will be used in the calculation. And I'll show you how to do that calculation now. So you look up the number of members you have combined in parallel, that NCOM value, and the total number of parallel members in the system, NCOM times NMEM, in table 2.7. This will give you values for the factors G31 and G32. Simple table lookups. Once you have those values, then you plug it into equation 2453, reproduced here. So in the example image on the screen here, I have 4 parallel members. So N sub mem is equal to 4. And each of these has 3 members combined. The NCOM is equal to 3. So for this example shown on the screen, I would have a G31 value of 1.20, and NCOM times NMEM is equal to 12. So, and G32 is equal to 1.33. So 1.33 and 1.20, I'd plug those into the equation shown here and get my K9 value. The other parameters in this equation, S is the center-to-center spacing of your parallel members, and L is the effective span length. Just to note, that's a span length. It's not necessarily the same thing as the total length of your beam. So just make sure you're using the span length when you're calculating this. So as far as the number of fixings that you need when laminating 2 different beams, unfortunately 1720.1 doesn't actually give guidance on this. It leaves it pretty much up to you as to how many fasteners, how many fixings you need to qualify as laminated. The only guidance a standard gives is it says all of the laminates must have the same deformations under load. So use your engineering judgment with that. Do some calculations for exactly what the deflection is and how strong and stiff your connectors are. Well, unfortunately, the standard doesn't give you any particular guidance beyond that. You then have some modification factors that you need to make for serviceability. So for each service load case, you have potential J2, J3, or J6 modification factors you need to calculate as well. Those are for creep or moisture content. When you're designing a beam, probably only deflection is relevant, but I want to list everything on this slide. So I'm showing you extension for shrinking or stretching as well. So we need to calculate J2 and J6 for long-term deflections, and you need J6 for short-term deflections. So those creep factors, J2 and J3, these amplify the long-term deformations. So table 2.4 gives you a duration of load factor and serviceability for various durations of the load that you're applying, duration of action, as well as for different moisture contents of your beam. You'll notice that this table only has 4 values. for 2 different moisture contents and 2 different durations of action. You are supposed to interpolate based upon the logarithm of duration for any duration that's between 1 day and 1 year, and you interpolate linearly for moisture content between 15 and 25%. Now, that's a bit of a pain of a calculation to make, but it is a very precise calculation. Unfortunately, while that calculation is very precise, the standard's actually pretty vague about what the inputs are supposed to be for this. So one note I'll call out in particular here is it says that the duration of action specified for the calculation of design capacity aren't intended for deformation. So in other words, the durations used for calculating K1 aren't intended for J2 and J3. But the standard doesn't give you any other guidance as to the durations you should actually use for J2 and J3. It just tells you what not to use. That said, it should always be conservative to use the durations that are designed for K1. It may be a bit over-conservative, but you should be safe doing that. The standard does also say twice in notes that it may be unconservative to calculate J2 and J3 per the procedure that they tell you for collapse susceptible unseasoned hardwoods. So collapse susceptible has to do with how much the timber will stretch before it fractures. Specific species are collapse susceptible or not. I'll refer that to you to look up whether the species you're using is or not. But if you are using a collapse susceptible unseasoned hardwood, the standard doesn't actually give you an alternative method. It just says this may be unconservative. So use your engineering judgment for those. Maybe look up some research if you are designing an unseasoned hardwood. Definitely don't design your long-term deflections to 99% usage for unseasoned hardwoods. But unfortunately, this is left up to you. The standard doesn't give you further guidance on this. For moisture content, that J6 factor, this factor penalizes LVL members which are not protected from moisture. So for LVL timbers, you use the equilibrium moisture content, which as a reminder is the average moisture content over a 12-month period, and calculate the J6 value based upon the formulas given in table 8.1. So shown on the screen here. For anything else, for glulam's, F grades, any other timber grade, your J6 value is equal to 1.0. There is no adjustment that you need to make with J6 for anything other than an LVL. So that's all of our modification factors, and that's about half this presentation. Now we can move on to actually calculating our capacities. So flexural capacity calculation is a multi-step process. It's because of that K12 modification factor. I'm listing in quotes here because I don't think it's quite a modification factor. It is specific to each design. For this, you first calculate the material constant, rho sub b. This constant relates to how susceptible the particular timber grade you're using is to buckling. Then you calculate slenderness coefficients, S1 or S2. These relate to the effectiveness of the lateral restraints you're providing to your beam. Finally, you put those two together to get your stability factor, K12, and that factor relates to the overall lateral torsional buckling capacity of your member. Finally, you can plug that all in and you'll finally get your actual bending capacity, M sub D. So first, the material constant here. There's a lengthy and very precise calculation that you can do in Appendix E of AS1720.1 that will give you a really precise rho sub B value. But those formulas are dependent upon the factor R, which is the ratio of, quote, temporary demands to the total demands on your member. But That ratio can vary not only by what load case you're considering, but also can vary along the length of the beam. Like if you have a concentrated load on the left side of your beam, then the ratio of temporary to total demands might actually vary along the length of the beam. But in total, the worst case difference is about 5%. So usually no one actually bothers to calculate the rho sub b value that precisely. It's usually not worth it to do so. So usually you can just look up in table 3.1 for F, MGP, or A grades, or table 7.2a for glulam grades, what your material constant is. These tables assume an R equals 0.25, assume that ratio is 25%, and that is conservative. You never need to go lower than that. So you can just straight pull your rho sub b value from these tables for most timbers. For LVLs, you have a formula that you're given, but you can always conservatively assume an R equals 0.25 in this formula. So just plug in an R equals 0.25, plug in your characteristic modulus of elasticity and characteristic strength and bending, and that will give you your material constant. Slenderness, your S sub 1 or S sub 2 values. There are several different cases depending upon exactly what your restraint looks like as to what your S sub 1 or S sub 2 value will be. The first couple cases are if you have discrete restraints. So first, if you have discrete restraints and are loaded on the compression edge of the timber, then your S sub 1 value is this top formula, which is a function of the depth and breadth of the beam, as well as the L sub AY value, the center-to-center spacing of the discrete restraints that you're making use of. Plug that in, there's your S sub 1. If you're loaded on the tension edge, that's a little less conservative, so you have a different formula that you make use of on the bottom of the screen here. Next, if you have continuous restraints. Now, very few things are actually purely continuous in timber. Probably you have nails or screws at some discrete spacing, but if that spacing is frequent enough, it qualifies as continuous. So the standard gives you a formula of if your L sub AY is less than the formula given at the top of the screen here, L sub AY over D less than or equal to 64 times the B over rho BD squared value, then it counts as continuous. So if you have continuous restraints along the compression edge, then that's your ideal situation. That effectively restrains any lateral torsional buckling, and S sub 1 is equal to 0.0 in that case. If you have continuous restraint along the tension edge, a little less advantageous again. So you do actually have a formula for S sub 1. It's going to be relatively small, but it's still going to be non-zero there. If you have the slightly more complex situation here of continuous restraint along the tension edge, but with discrete torsional restraints, then you have a slightly more complex formula shown at the top of the screen here for your S sub 1. And if you have bending about the minor axis of your timber here, you're generally not going to be able to buckle out to the side. Generally, the timber is going to only want to bend in the direction about the minor axis. So S sub 2 is equal to 0.0 in that case. If you have any other type of situation, there are more general equations given in Appendix E6, but those are much more complex equations. They can sometimes be a little bit more conservative. So if you're trying to squeeze every last bit of capacity out of your timber, then you can refer to Appendix E6 and do the longer equations there. But it's, again, generally not worth it and requires some more inputs, some more parameters to consider. So generally, you don't need to do that when you are designing timber. So that will give you your rho sub B and your S1 or S2 values. And with those, you can calculate K12. There are three possible equations given in the standard based upon the product of rho sub b and S sub 1, based upon your material constant and your slenderness. So if that product is less than 10, then K12 is equal to 1.0, flat out. If it's between 10 and 20, then you use the second equation. If it's greater than 20, then you use the third equation. If you have bending about the minor axis, which would effectively give you a product of 0, then K12 is equal to 1.0. So any bending about the minor axis, K12 is 1. For those of you who may be more familiar with steel design, these equations are akin to saying whether the timber beam is compact, non-compact, or slender, going from top to bottom there respectively. If you're not familiar with steel design, don't worry about what I just said, but that's effectively what these equations are representing. So finally, once we have that K12, we can actually calculate the bending capacity here. So the bending capacity is the formula that I showed you on that early on slide with all the modification factors. So M sub D equal to phi times K1 times K4 times K6 times K9 times K12 times your characteristic capacity and your section modulus. So section modulus is just geometry. I've shown you a couple of the formulas here for a rectangular beam. You can look up what they are for other shapes as well. The only additional note here is if you're bending about both axes simultaneously, if you're bending about both the major and minor axes, then you calculate your bending strength individually using the same procedure about each axis. Once you have it for each axis individually, you plug those values into the formula shown here. There's also a lengthier formula, again, in Appendix E that's going to be a little less conservative, but usually you can just use the formula given at the bottom of the screen here if you are bending out both axes. So finally, we can go on to shear, bearing, and deflection, which are all fairly simple, so I'm just going to talk about them all at once. First, shear strength. It's a pretty straightforward calculation. It's just the modification factors we already have of phi, K1, K4, and K6 times characteristic strength and shear times A sub S. Now, A sub S is your shear area. It is not the gross area. For a rectangular member, it's equal to 2/3 times the gross area, 2/3 times the breadth times the depth. For round timbers, the standard gives you a formula. For other shapes, you can look up what that would be for whatever shape you're dealing with. You are allowed to ignore loads when considering shear that are within a distance of 1.5 times the depth of the face of a support, but it's really rare for shear to actually control a design in timber. So the standard gives you this thing you can take advantage of, but it's going to matter so rarely that I advise generally to just not bother with it. If you happen to find that shear controls, then maybe go back and consider it, but you can generally just ignore this clause and just straight calculate shear from the top formula there. Next, for bearing. Usually your bearing is going to be perpendicular to the grain. Most cases, it's 90-degree angle to the beam that you're bearing onto. If that's the case, it's a relatively simple formula. Again, just making use of modification factors that we already calculated, multiplying by the characteristic strength, multiplying by A sub P. A sub P is the area of bearing, and that is the gross area, so no reduction there. It's just a gross area. The only note I'll make with that is that your K7 factor may be different for different supports. So if you have one support that's at the end of your beam, then that K7 is going to be 1.0. If you have a support in the middle, then that may have a different K7 value. That may have a 1.15 K7 factor, for example, for your interior member. So just be conscious of which bearing location you're checking as to what your K7 value may be. Also note that bearing is not relevant for all types of connections. So if you have a bracket that you're making use of that attaches to the side of a beam, then you don't have to check bearing on there. Bearing is just an irrelevant limit state. Effectively, the same thing is going to be checked when you do your connection design for that bracket, but you don't need to do a bearing check. Next, if you have a non-perpendicular bearing. Simplest case is if you're exactly parallel to the grain, but you can also have an angled bearing that is somewhere between parallel and perpendicular. If it's parallel, then again, you just have one formula here. Phi times K1 times K4 times K6 times characteristic strength for bearing parallel to the grain. That is a different value than perpendicular to the grain, times A sub L. And that's, again, your gross bearing area. Just note here that K7 is not included in this. So you can never take advantage of any increase in bearing capacity for being parallel to the grain. If you have an angled member or an angled bearing, then you calculate individually the parallel and perpendicular capacities and combine them together in the formula shown at the bottom of the screen here. Just be careful when you do that, though, because your bearing areas perpendicular to the grain and parallel to the grain are going to be different, or are most likely going to be different. So in the example drawing shown on the right here, I've shown what A sub P and A sub L would be for this member. Because it's at an oblique angle, A sub P is going to be smaller than A sub L, because you take what's exactly perpendicular and what's exactly parallel to the grain. So calculate each of those individually, combine them together, be conscious of what your bearing area is for perpendicular versus parallel. Finally, going to deflection, your bending stiffness for deflection is simply E times I. Standard definition here. You can calculate deflections by whatever your preferred method is, using finite element analysis, using classical beam theory equations, 5WL to the fourth over 384 EI, for example. Calculate your deflections, and then you adjust them. So for short-term deflections, you have that J6 modification factor only. So your simple deflections multiplied by J6 give you short-term deflections. And then long-term deflections, you multiply your simple deflections times J2 and J6. Note, however, when you do that, J2 is specific to each load type, not to a global load case. So you should do this multiplication before factoring your load cases. It is conservative if you want to make your life a little bit easier with this. You can just take the worst case, J2, and multiply that by the entire load case result for your long-term deflections. It's not going to make much difference. Usually for you're going to be governed by gravity, and gravity, both permanent loads being permanent and long-term imposed loads being long-term should have a duration greater than a year. So your J2 would be the maximum anyway. Where it's going to make a difference is for long-term deflections that have to do with snow or other loads such as that. So you can take advantage of J2 being per load type, but you can conservatively just assume the largest J2 and be done with it. So that's a total design for a beam. I'll go through a couple of example calculations now, both a simpler and a more complex one. So our simple example here is going to be for a simply supported beam. I'm going to assume that this is a roof bearer in a residential house. So that means it's an R2 roof according to AS1720.1 for a residential house, which means imposed load is 0.25 kPa. Because it's a roof bearer, then we're going to assume that it's a primary structural member, and that makes it a category 2 member. We're going to assume a tile roof, which as per the standard is a permanent load of 0.9 kPa. It's going to be restrained by the roof trusses, which we're going to assume are spaced at 600 millimeters on center, which means discrete lateral bracing at 600 millimeters on center, a 2-meter load width, and we're going to assume a 90 millimeter bearing length of those supports. What we're going to end up finding, and I'll show you how to get to this, we're going to end up finding that for an LVL, the most efficient LVL member will be a 300 by 35 E-beam manufactured by Westbeam. I know I'm not trying to promote any particular manufacturer here. I'm just going to arbitrarily select Westbeam here as the manufacturer that I'm going to design to. So, show you how to do those calculations. And I'll show you how to do it using the ClearCalcs platform. So I'll open up my web browser, go to clearcalcs.com, log in, and I'll create a new project for this. So within our platform, we allow you to have different projects that you can name whatever you'd like, give project numbers, keep track of your client, give a date, keep track of your project address. And we do support building standards from the US, Canada, and Europe as well, but obviously we're designing to Australia here. We can set some of the global options here for the structure we're designing for in the project defaults. So the rafter or truss spacing we said was 600 millimeters. That is our default here, so we're just going to keep that. The roof we said was going to be a tile roof. So that's giving us a 0.9 kPa permanent load for the roof. Standard residential roof in a house is an R2 type roof. So that gives us a 0.25 imposed load. We can expand anything shown here to see exactly what checks are being done, see descriptions and references for all of them. Oh, excuse me. In order to quickly design everything, we can add some preferred sections here. These are sections that will auto-design for or that are going to show up at the top of the list to make our design easier. I can add them individually on the Add Section screen here. But I've also already put together a bunch of them in another project here. So I'm going to pick from the Westbeam catalog here. I'm going to say that Westbeam is the preferred supplier for this particular project. So I'm just going to copy the sections from that other project. That's going to put those into my preferred sections list here. Next, I'm designing a roof bearer timber beam. So I'll click on timber beam. I'm given a choice of a lot of different types of beams. I'll select roof bearer here. We said that our beam was going to just be 1 ply, discrete restraints at the compression edge, as would be something that's supporting trusses. Length of bearing of 90. Total length of 3,800 millimeters, and we can see that the default MGP10 that was selected here now no longer works. I can scroll down. We can see that because I've selected a roof bearer, we automatically assume that that's a primary structural member. So the default is automatically set here to category 2 for the structure category. I'll just keep the default deflection limits as they are. And the distributed loads are pulling the magnitudes off of that project default sheet. So 0.9, 0.25 are already pulled in here, and that's applied along the entire length of the beam. Everything else we should be able to leave. This is major axis. You do generally want to include self-weight. The character of the imposed load, again, just to be clear that this input does not actually affect the magnitude of your loads. What it affects are the factors that are multiplied onto your specific load case. I will talk about those in a separate webinar that we'll have upcoming, talking about loads and load combinations. But this doesn't affect your magnitudes. It affects factors that are multiplied in the load cases. Now, just to keep this is a simple example, I'm going to remove my wind loads. I will keep the alternate imposed load, but I can change that to 1.4 kilonewtons, as you only need 1.2 for a roof. And now I can see my shears and moments plotted for 1.2G and 1.5Q load case here. You can see that, of course, we're failing with the default, but we can quickly select the best possible member by clicking this auto size button. And that's going to automatically pick out the best possible size beam here. So that's picked out a 240 by 35 West beam E-beam. And we can see that has 97% utilization. You can't get a whole lot better than that. Our governing limit state is long-term deflection, where we're almost at 10 millimeters long-term deflection. And if we want to take a look at what exactly that looks like, we can look at the long-term service case, where we can see what the envelope is for all of the long-term service load cases. And we can see what the specific load case that I've selected is, G and QLT in this case. We can also scroll down and see all of the member properties. We can look at all the modification factors that are considered here. By default, we assume that the equilibrium moisture content is going to stay at 15% or less. The only time this really changes, as we discussed earlier, is if you have an unprotected outdoor beam, for example. You can look at some of the notes related to that if you expand the section and refer the clause specifically there. That results in a K4 equal to 1. We are designing for most of Australia, so K6 is equal to 1. A bearer typically does not have multiple parallel members, so we can't take advantage of K9. That's equal to 1. But this is a relatively thin member. So K12 is actually calculated as 0.8. It's relatively low. So we do have a bit of a loss in moment capacity there. We show you what all the possible J2 values are. We are internally taking advantage of whatever the J2 value is for each load type here and multiplying each of those in. See all the results for the load cases, every load case that's being considered. Look at the unfactored loads. Bearing has its own section here where we can see each of the individual support locations. We can see that K7 was calculated as 1 for both of those because they're both end supports. And see what the bearing utilization is for each of those. And you can also look at the deflection for each of the spans. We only have one span, so this isn't too exciting. Look at that section. You can also expand out and look at the detailed calculations and see every step of the way in here. So we can see, for example, what all the governing load cases are that we've found to be controlling for each of these. So as is common, the moment is governed by 1.2G plus 1.5Q. That's the most common thing that's going to govern. Well, you'll notice here that bearing and shear are actually governed by 1.35G. So this is actually an example of a case where we have a relatively high dead load. So because of that K1 factor, we are governed by the 1.35G load case rather than the typical 1.2, 1.5, even though that's higher. So we're taking that into account. You do need to be careful of that, as we discussed, when you are doing your own calculations. So that is our design for our simply supported beam. Next, we'll go back to our presentation, and we will do a design of a complex beam. So for this, we will assume a 10-meter total length for the beam. We'll assume this is a floor bearer this time. So floor bearer running along probably the whole length of our house. Because it's a floor bearer, because it's so long, it's definitely a category 2 member. I'm going to assume a load width of 2 meters, and we're going to assume that it's restrained at 450 millimeter on center joists. Because those joists are going to be on top of the bearer, that means that we have discrete restraints at what's typically the compression edge. So I'll select that as the option. And again, I'll take a 90 millimeter bearing length. This time, however, I'm going to design a custom beam. I'm going to end up with a 3-ply 250 by 45 radiata pine, but I'll show you how we can get there in designing our custom beam. So going back to ClearCalcs, I will add a new calculation here for a floor bearer. So we said this is going to end up being a custom beam. So I'm going to select yes for custom here. And you'll notice that some of my options changed here. I now have radiata pine. I have my species selection. We're going to assume a seasoned radiata pine. Just keep some of the selections a bit simpler. Timber grade, I'm going to say it's an F17. And we said it was a 250 by 45. But I'll leave NCOM as 1 and come back to that later. This is a total beam length of 10 meters, discrete restraints at the compression edge. On that project default sheet, and if you click on the cell, you'll see that we're referring to project defaults. We're pulling the default joist spacing of 450 millimeters for that. So LAY is equal to 450 millimeters. We need to change our support locations though. So supports are at 3 meters and 8.5 meters. And we said length of bearing is equal to 90 for all of these. So I will set those. Note that in our deflection limits here, we automatically had added an additional row here for the cantilever deflection limits. So these are by default notably larger than for an interior span. So L over 150 for a cantilever as opposed to L over 300. But this can be changed for short-term, long-term, or imposed load deflection limits. Again, this was a primary structural member, so category 2. We're going to keep our load simple. And we said that load width was going to be 2 meters for our floor load with a 0.5 permanent load and 1.5 imposed load, KPA. We said, however, that we're going to put our beam from the first example on top of this one. Now that wouldn't usually happen. You wouldn't usually have a roof bearer on top of a floor bearer, but just to show how this would work, I will link to reaction, click on that chain link icon next to point loads, select the location of the support. We said that was going to be located at a location of 1.5 meters along the beam. And now we can see that the load from our other beam is now on here. You can see on the diagram of all of our loads there. This is a house we're designing, so I'm going to switch the character of imposed load to residential and domestic floors rather than an office floor. That gives a slight advantage as well. And again, we said we're going to keep things simple, so ignoring any wind loads. The alternate imposed load needs to change location. So that for, if you have a cantilever present, the standard tells you that that alternate imposed load needs to be at the end of the cantilever. So I'll put it there. Has a magnitude of 1.8 kilonewtons according to AS1720.1. And that will then show up on my diagram here. So yeah, that's what the alternate imposed load is. The standard AS1170.1 tells you that an alternate imposed load needs to be checked for the most extreme possible location for just about any beam. For timber, it makes a difference. We often don't bother with it in steel or concrete because it generally doesn't make a difference in steel or concrete. But for timber, we do need to consider that alternate imposed load. What it is trying to say is that if you have a relatively low distributed imposed load, you could still end up with, for example, your resident putting a big heavy bookshelf at one particular point along your beam. So that's trying to account for that big heavy bookshelf or that one big heavy thing at one location along the beam. So that's what the alternate imposed load is considering. It is not applied simultaneously. It is assumed to apply at a different time than the distributed imposed load. Internally, our software is taking that into account. Effectively, we're doing two separate load cases for the distributed imposed load and the alternate concentrated imposed. So if I were designing a floor joist, then I would have continuous restraint. For this, we said this was a floor bearer. So bearer being the large beam underneath a floor joist. So the bearer is going to have only discrete restraints. If I were designing a floor joist here, then yes, that would have continuous restraints. So again, we can scroll down in all of this, expand all of our sections. We can see that we have a lower capacity factor being used because we have that category 2 member. It's a seasoned member. Because it's interior, we're still keeping the default equilibrium moisture content of 15%, which gives us the K4 of 1. Again, it's a bearer, so there aren't parallel members here. So for now, K9 is equal to 1. And it's not a particularly thin member, so K12 ends up being equal to 1. Point out that for bearing, we now have multiple locations, and we have two locations that are interior. So we have a bearing factor of 1.1 at the 3 meter and 8.5 meter locations. It's automatically calculated out here. And then deflection, we have 3 different spans now shown as well, so you can look at what those deflections are for each individual span. Now, at the top of the screen here, you can see that we are way above the maximum that we can support for this beam. Everything is in the red. So I'm going to increase that income value, put 3 laminates here. You can see the diagram now changes here too, and shows those 3 laminates next to each other. And now everything is green or orange. We're still governed by long-term deflection. That's very often going to be the thing that's going to govern your beam design, long-term deflection. But you can see what everything else ends up calculating out to as well here. And you can see that we are showing those full formulas here. So for example, moment capacity, you can see that this is M sub D equal to all of our modification factors and the characteristic property and that Z section modulus. And you can expand out anything here to show what those values are. We show you what the reactions are at each location. So ultimate maximum, ultimate minimum reactions, as well as your pure dead load and live load reactions. If you are unable to read anything, as you can see, you can hover over the arrow and it's going to show you in a pop out exactly what those values are, but usually you can just read it off of the diagram. One other thing I will point to is that we give you the option of showing plots including or excluding that K1 factor. So you can, by default now, we are including the K1 factor, which is showing you the final demands that you would compare with the final capacity, including the K1 factor. But internally, and a common way that you might deal with the K1 factor being different for every load case is to rather than calculate the capacities and demands as the standard says, calculate your demand divided by K1 and your capacity without the K1. So effectively dividing both sides of the equation by K1. So demand and capacity both divided by K1. So we do that internally, and we give you the option of seeing that. So you can, this is now showing you all of the load cases. And because it's comparing to the same capacity, you now have one capacity because K1 is removed from the capacity. You can now meaningfully see an envelope of what all of the different load cases are. So for example, I can see that 1.35 G load case is less than the maximum envelope here. And you can see that that's not governing. And you can see how it is governing for 1.2 G and 1.5 Q. Just scrolling back down, since we did make this a laminate of 3 members, that strength sharing factor is now equal to 1.2. So we're automatically calculating that out. That's our more complex example. And you can follow through with that. We will be making the PDF of these examples available as well when we distribute the video and slides for this webinar. So going back to our presentation now, let's conclude and take any final questions. So summing everything up, AS1720.3 is a self-contained interpretation of the timber and load standards. It replaced AS1684.1 and is for conventional residential timber framing only. AS1684.1 is a defunct standard, chuck it in the bin. 1720.3 is the simplified standard. It's limited to only standard timber grades, limited to buildings that are 2 stories or less with the maximum 3-meter walls, and buildings with a maximum dimension in any direction of 16 meters. The beam design checks that you need to do to check your beam are for characteristic properties. First, look those up from the tables, either in the standard or from your manufacturer for LVLs. Then you calculate out your modification factors, your K1, which varies by load case, and then your K4, K6, K7, and K9 values. Then you, for flexure, for bending, you calculate your material constant, rho sub B, your slenderness, which relates to your lateral restraints, S sub 1 or S sub 2. That gives you your stability factor of K12. And then finally, you get to your overall M sub D capacity. Shear is simply multiplication out of modification factors and the characteristic values to get V sub D. Do remember that the area for shear is not the gross area, but for a rectangular section, it's equal to 2/3 of the gross area. For bearing, usually you are bearing perpendicular to the grain, and for that, it's just a simple multiplication of the modification factors. If it's parallel or angled, you have a little more work to do for calculating out what the, in particular for an angled bearing, do remember that your A sub P and A sub L are different values. Deflection, you have short-term deflections that contains the J6 modification factor, but does not contain J2. And your long-term deflections, which do include J2, that creep factor, as well as a J6. We then performed a couple of examples for simply supported and complex beams as well. So any questions, do feel free to ask them now. And any more involved questions as well, I'm happy to answer those. Happy to answer any questions about how to design a timber beam or any questions about the ClearCalcs platform as well. As you enter those in on the Q&A here, I'll just add that we already have a fairly large suite of calculators available in our Australian offerings for timber, steel, cold form steel, concrete, connections, footings, and cantilever retaining walls. We have some custom section support, especially for timber, but we just started adding it for steel and cold form steel as well. Right now, those are independent calculators, but we will be linking those into the design calculators as well. So you can make use of those directly for steel and cold form steel. We're also working on some other more advanced connections and retaining walls as well. Do watch our emails for more free webinars that we offer upcoming, as well as information on designing other types of members and connections. So now it looks like we've gotten a few questions coming in. One note that AS1684.2 does provide information on specifying the laminations. So thank you very much for that. That does partially answer a question I incompletely answered first. Yes, that is still current. AS1684.2 you can use here. So yes, if that defines how frequent your fasteners need to be and what type of fasteners you use, you can refer to AS1684.2. So yes, do refer to that. Note that 1684.2 is only relevant for short structures for two-story houses and other restrictions that it specifies in its scope. It's not relevant for larger structures. So for larger structures and what counts as being fully laminated, you probably use that as a guideline, but it technically does not govern. Would we be able to do a webinar for timber joints in the future, such as timber bolts? Yes, absolutely. Definitely happy to do that. We do want to upgrade our connection calculators. So I will do that first. Expect a webinar on timber joints in another month or two, probably, after we upgrade those connection calculators. The upgrade to those connection calculators is just going to make things a little bit clearer. You're going to have a drop down, for example, saying that I'm designing an L bracket or I'm designing a nail plate or something like that. Just be a little bit clearer about what the actual connection is you're designing. Right now, you have to use some engineering judgments in our calculators to figure out which limit states are relevant for the particular connection you're designing, but we will be automating that. Once we do that, we'll do a webinar on timber joints. As far as steel beam design, we did actually already do a webinar on steel beam design, and we'll include a link to that when we email out the recording from this webinar as well. So we'll get that out to you. We did already do a webinar on that. You should be able to look at our YouTube channel and Google that and be able to find that. Are masonry calculations in the pipeline per AS1720? Yes, they are. They've not been terribly high priority for us. We've not heard a lot of requests for them, but one advantage to our platform is that we constantly roll out updates, and we do that based upon what we hear requests for from our customers and potential customers. Given the request I've heard here, definitely happy to bump the priority for that. So yeah, we'll try and get to masonry calculations soon. Also about timber flitch beams. Yes, that's also on our to-do list. I've heard a couple more requests for that, so that is going to take a little bit of precedence over masonry, so that will probably come out first. Yeah, timber flitch beams will be adding to our platform sometime in the next couple months, most likely. Yeah, thank you. And that looks like all the questions that I have right now. If you have any other questions, I will remain on the line for another couple minutes. But otherwise, that is the end of this webinar. I'd like to thank you all for joining us. Again, do keep an eye out for further webinars that we will provide for free. on how to design other types of members and connections. Yeah, so a question about concrete sleeper retaining walls. Yes, we have been working with a geotechnical engineer to try and get those in. We got a bit delayed with that after he got held up in immigration, unfortunately, leaving Australia, not entering. But yeah, that will be coming in. How far off are we for that? A little bit hard to say. We definitely want to get concrete and an upgraded timber sleeper retaining wall into our platform as soon as possible. That could be anywhere from a month and a half to probably worst case is about 4 months off. I'm sorry, I can't give a more precise answer to that, but yeah, that is in our pipeline. We do know that's a fairly high priority for getting concrete sleeper retaining walls in. So what's considered an appropriate eccentricity for the design of vertical studs in a wall? For designing a vertical stud, there is a minimum eccentricity that the standard says, and I don't remember off the top of my head what that is. Yeah, there's a minimum eccentricity that is recommended in the standard. Unfortunately, I'm going to have to go refer back to the standard and get back to you on that. We'll try and include that in our follow-up email to this webinar. Yeah, there is a minimum eccentricity recommended just to account for people hanging something heavy on the wall or construction being not exactly 100% 90 degree or slight flaws such as that. As far as other eccentricities, obviously just whatever is physically designed for. If you have an eccentricity, if you're attaching a weight to the edge of the wall rather than straight onto the top, then your eccentricity is going to be equal to the breadth of the stud divided by 2. So yeah, use what's appropriate or refer to the standard for the minimum recommended. So are the AS1684 table supplements still valid for quick design checks? AS1684.1, no. You should just be using AS1720.3. 1720.3 does have similar table supplements for quick design checks. I'm not sure exactly what the questioner here is referring to, which tables, but I think the ones you're referring to are in 1720.3, and those are the ones that you should be using for your quick design checks. There are some table supplements as well in parts 2, 3, and 4 of 1684. Those are fully still valid. Those you can definitely refer to. But yeah, generally you should be able to just bin your 1684.1 standard as it has been technically replaced by AS1720.3. So when will we have wind beams for, yeah, when will we have, we actually already have wind beams. So I'll just quickly go to add a new calculation here. So when I click on timber beam, you'll see wind beam is an option here. You can already select that. When you select that, you default, you'll see that the primary loading is defaulted to being about the minor axis. And you can select most members here. I will note that LVLs tend to be inefficient in minor axis bending. Probably don't want to actually be using them. If you do have to use them, we only have characteristic properties from some manufacturers. Not all the manufacturers have provided us characteristic bending strengths in minor axis bending for their LVLs. So in those cases, we unfortunately can't do the calculation for you. Those manufacturers say that you should contact them directly if you're doing a minor axis design. But you can always do a wind beam design for any MGP, F, glulam, or A grade. And that's fully 100% supported within our platform. And then there's a very specific question about bolted joint design for one particular table in AS1720.1. I'm going to get back to this question in our email follow-up for this webinar. I'm not that familiar with the standards to know exactly what table 4.10a is. So I'm gonna have to go refer to that, and I will answer that question in our follow-up email for this webinar. So yeah, thank you very much. That looks like all the questions that have come in now. Again, I'll just stay on for another minute. Now the question queue is cleared up. But thank you very much, everyone who's attended here. I hope this was helpful to all of you, and do take a look at ClearCalcs. We think we have a great platform here, and love to see as many people join as possible. All right, looks like that's it. Thank you very much. If you do have any other questions, feel free to use the help system within the ClearCalcs platform, and we can get back to you with any other questions through the help system. Thank you very much. Bye.